So hello. So today I'd like to finish this topic of numerical integration. So first let's pass through some particular topics. First is adaptive methods. So this is variation of the usual method, which can be very efficient, but often requires some extra work. But also it is implemented in many already used software programs. So essentially the idea is that imagine that you use a composite rule for the integration of a function. So you have a function. But function is something like this. Then you integrate it in the interval between a and b. So what we did before is that we used uniform mesh. So we used the splitting of this integral into the equal interval of the equal subintervals, and then used these points at x1, x2, x3, and 4. And then within each subinterval, you may use, for example, the quadrature or something like this. But if the function has very strong variation between, so like very intermittent variation, so in some places it's almost does not change, in some places it has huge variations. So this is often not effective because the error, the error of the computation will be defined by this interval where it varies a lot. So it does matter that you compute it very well in the other part, but the error will be all in this piece. So there is a very easy way how to overcome this problem is just you, in a place where it varies more, you put more points. Here you may want to use short intervals like this. Here you use 2 intervals. And the rest here maybe also. And the rest is fine. Right? So essentially you would put more, you split the intervals to the smaller intervals at the places where it's necessary. So something very, very simple. So the usual setup that you can encounter in description of many methods, we most already implemented in packages like MATLAB, Python, or whatever. So usually you have to set 2 things. First, error tolerance, let's say epsilon. Often you specify several tolerances, so it can be absolute and or relative. So you define some error tolerance, and then it's also useful to put minimum. Essentially, it is almost always a part of the method, so minimum interval lengths. This is because sometimes, for example, if the function is discontinuous, maybe you never reach the error tolerance that you want, and then the method will start to decrease. The interval never converges, so it's useful to put a minimum length. And then the method is the integration step. So the method is that you do integration step, then you estimate the error, on this step. So you put a step, let's say, of the length h. Then you estimate the error at this step. This estimation of the error can be done in different ways, but I think the most popular way is that you just compare the computation on this interval h with the same computation with twice smaller interval. And if you take twice smaller interval, it's a high order method, so the computation with a twice smaller interval is much more accurate than the previous one. So the difference is essentially the error by order of magnitude, for sure. So you compute the error, and if the error is bigger than epsilon, no? And your step h is bigger than delta, then this computation is not valid because it's not accurate and the step can be increased. So then what you do, you recompute with a smaller interval, which you take like maximum between half of the interval and the smallest possible value. So dividing by 2 is just first simplest way. You cannot, instead of dividing by 2, depending on how you estimate an error, you may be, instead of dividing by 2, may go to some better interval than just half, but this is one of the ways. So you compute on one interval, estimate an error. Error is okay, and you go to the next interval, estimate an error. You go to the next interval, poof, here the error is too large. So you make half of the interval. You compute, estimate an error, it's still large. So then you go to the smaller one. And at a certain moment, error is okay, so then you continue. And in the same way, if the error is too small, you can, at a certain moment, you can start increasing the interval. Not only decreasing, but also increasing. So in that way, you have an adaptive step. And certainly this allows you to keep at the same tolerance, but with fewer steps. So that sometimes much fewer steps. Okay. So this is one topic. Another topic is exact integration. Exact in the sense of exact interval bounds. So that's, well, that can be important in various situations. One, if you want to know your integral not with certain accuracy, but exactly where the interval, what is the value of the integral, to have some definite information. So, for example, you should want to know that the value of the integral is between certain two numbers, which you maybe want to make close to each other. So some definite information, and this is both practical, but also it is what is usually used in computer-assisted proofs. So whenever you prove theorems with the computer-assisted proofs, so often this is a way. So you just, if you take an integral, you make sure that it's exactly to compute the interval where it lies exactly, and then you can make some conclusions. So this is rigorous. So just to give an idea, so what you do is that, for example, use a formula for a quadrature. So in the interval, so let's take interval between a and a plus h. That's the interval. Short, small interval of size h. So what you do, you estimate the integral between a plus h, f dx. So it is, so I'll take this two-point method. So how you do it, it's, so it should be, f of a plus like this. Half minus 1/3, yes. Just check if I'm correct or not later. So this is what's called two-point Gauss-Legendre quadrature. Just we was always writing it for interval between -1 to 1, and I tried to make it for arbitrary interval. Okay, should be correct. And then what's important is that we have exactly the extra term. So the extra term is, so it's fourth derivative at some point divided by 135, and then it should be multiplied by to 4. I think this should be this. I'm trying to readapt the formula from -1 to 1 directly. So what is here is that psi is some point in the interval. So we just have formula which is exact. So the first part of the formula is used for calculation. The second part of formula is an arrow. And now what you just do, you take this arrow and estimate it exactly. And estimate this error term exactly. So how you do this? Essentially, you need to know have some information about the function, of course, and how it varies. But usually, for many functions, if you take interval h small enough, you can guarantee certain limitations for the variation of the function, and then you can guarantee that, for example, the fourth derivative does not change more than certain quantity. Then you just take any point plus this bound. So usually there are ways how you do it. And then if this belongs to some interval, you automatically find an interval to which belongs the function, the interval. So this gives you exact interval. For the interval. So doing this step by step, you may come to the exact estimation of the interval, and taking steps sufficiently small, you compute it whatever accuracy you want, but exactly. So you know that it's between two numbers, and this is exactly there. So that's second method. So now this is all one-dimensional, and we were discussing that that all the formula, they extend to multidimensional integrals, and multidimensional integrals, they are useful in many cases. So that let's check first the question: what is an arrow? Arrow in multi-dimensional integration. And this computation of this arrow will motivate one more numerical method that I'm going to give. So let's just take composite trapezoidal rule. So this is what we probably will use as if you do the first attempt to make an integral. So that's some simplest way to do is you take a function, split into equal intervals, and just within each interval you approximate function by the linear one, and then this area belongs to this linear approximation is trapezoidal rule, and we know what it is. So for one dimension, like here, so this is a function. So let's take function between, just interval between 0 and 1. Take 0 and 1. So it's what? It's a sum over, so we take, let's say, n intervals. N or m intervals. N intervals of size 1 over n each, right? In that case. So what it is, the integral is so this area is exactly the sum over all endpoints of the interval with some weights wi by the value of the function at this point I over n, right? And the weight is, it's 1 over 2n at endpoints and 1 over n at other points. Right? So this is how you do. You take every point inside with one weight and endpoints with another weight because they just correspond to these thin regions. So this simple, very simple trapezoidal rule that you apply, and it's second order. So for larger dimension, you do essentially the same. For dimension bigger than 1, so integral of the function. So let's take it for now just into integral in the cube of size 1. So of d variables, right? So what it is, it's essentially you now apply just the same trapezoidal rule, but in each variable. And then you get the second order method. This is approximate, right? So you approximate it with this trapezoidal sum, but now you do it in each variable. In principle, you can have different number of points, but we take this here just the same number of points in each dimension, and then you get weights which have to be multiplied, and then a function computed at each node. So this is how you compute trapezoidal sum in higher dimension. So error is the same, it's second order. Right? Error is the second order, so what we can do, so if the function, so it's second order if the function is C2, right? So if the function is C2, so in this case it should be C2 on a cube. So then the error is second order, so it's no good. That was why it was used different. Sorry. So by capital N, we will use number of operations. So let's use M here. M intro, it's just the same, but now we just put M. For M. Sorry for this. Okay, that's good. Here. So the error is what? Error is second order. So it was M in power D. Oh, no, power 2. Second order. Minus 2. H in power 2, and H is 1 over M. But number of nodes that you can have to use in this operation, in this computation, which is the same as number of operations. Yeah, because each node, computation of each node is certain fixed number of operations. So the number of operations is, you see, it's M in each dimension. So called N is order M dimension D. M in each dimension, so number of operations that you have to compute this integral is order of MD. So which means that now you can relate directly. Let's take. So we can take relate directly epsilon with N. And so what you get, so you can make the two-side estimate. So the error we can approximate in terms of number of operations. It will be N minus 2 over D. Or you can do the vice versa. So how many operations you need in order to achieve certain error. And then it will be epsilon minus D over 2. Just assuming that nothing is degenerate, so we deduce these two relations. The second is, this is just inverse. One is inverse of the other. So now what you can see is that in principle, it's not very good. It's not very good news. For example, Imagine that you want an error, a reasonable error, like 10 minus 3, like 0.1%. And you want to compute integral in dimension 10. And it's not difficult to imagine a situation when you want to do it. So some integral with respect to 10 different parameters. So then, with this method, with the trapezoidal rule, your number of operations will be of order, so what it will be, this epsilon minus d over 2. D over 2 is 5, and times minus 3, it will be 1015. So huge. So it's already hardly feasible with computers. So just already simple integration, but with high dimension, it becomes unfeasible. So that's why we will take a different method. So how to compute the question? How to compute integrals for large dimension. And dimension, sometimes you need huge, really. It depends on the application. So this is what comes Monte Carlo approach. The Monte Carlo method. So what you do, so we will already take the high dimensional version. So imagine that we want an integral of a function in dimension d. So x is in dimension d, and omega is some area in dimension d. So we have this d-dimensional d-dimensional area, and we want to integrate function in this domain. And d is huge. Maybe we compute some problem in, I don't know, physical chemistry when dimension can be. Each dimension is degree of freedom of molecular, and molecular has 100 atoms, so this can be integral in dimension 200, for example. Okay, so how you do it? So now consider x as a random variable, uniformly distributed. In omega. So in uniformly distributed omega, it just simply means that probability density function is, so we call it rho of x. So its probability density, it will be 1 over integral dx, so 1 of the over the volume when x is inside the volume and 0 otherwise. So simple probability density, so the point can appear everywhere with equal probability inside the volume. So now we will approximate the function, the integral of the function. So what it is, it's exactly the integral of a function times density, now over the full domain. And it's exactly the mean value. Let's call mean value by the mean value, expectation. So now, how you compute expectation? So your expectation you can compute just directly. So essentially from a definition. So having n random IID, so independent identical distributed samples. Let's take x1, x2, xn. We compute we approximate the mean value as one, as just mean, directly what called mean. So sum of the values on these points. So what's the idea behind the, so this is just, it follows that, we will see how exactly it follows. Of course, the bigger you take n, better you approximate. So the idea is essentially close to the idea of the previous multidimensional method. So the idea is that if you would use the trapezoidal rule, so what you do is you use a mesh and compute the function at nodes, right? So, and then take a sum. So this would be trapezoidal rule. So here, instead of this, so for high dimension, this turns out to be heavy because you need to put a lot of points. Every dimension gives you much more points in each direction. So instead of this, you take the same volume. Okay, doesn't look the same. And what you do is you randomly put points here. It's 1, it's 2. Randomly, but such that it's uniformly distributed. So they appear everywhere with this exactly the same probability. And now instead of summing the function at this regular set of points, you sum the function at irregular set of points. And that's a whole difference. And we know that in both cases, they will converge. More points you take, they will converge to the exact form of the integral, but they will converge differently. So in the first case, we know how it's converging. So now we need to compute how it converges in the case of the random points. So this is what's called Monte Carlo. Monte Carlo, it's like you're playing the game. So you just take arbitrary point, take function, point, take function. So if you want exact value, how error estimate of this convergence. So let's recall the central limit theorem. It's probably the main thing you learn in the course of probability. And this central limit theorem tells you that in general, so a sequence, so for a sequence x1, x2. I don't want to put lower indices because they were coordinates. So for infinite sequence of IID random variables. So this is exactly IID random variables for which we take samples in order to compute the integral. So they are identical, independent and identical. So identical means that they have the same mean value with the mean which is called mu. So all of them have the same mean value. And all of them have the same variance. So variance, remember variance, it's by definition you take the difference between the variable and its mean, square it, and take the mean again. So this is variance. So it should be, it's usually called sigma square, so the sigma is the square root of the variance. So it should be finite. So for a sequence with mean and finite variance, the random, so we have that the sum, the finite sum, so take the sum of n, first n of them, and take mean average. So any average will converge to a certain distribution, which will be normal distribution. In order to have this normal distribution, so certainly you see this sum of independent variables divided n variables divided by n, it should have the same mean. So we already can subtract this mean. And also what you see that whenever n is larger, the value that this average will take, they will fall closer and closer to the average. So in order to have some sensible limit, we have to multiply by stretch it. So the correct coefficient is square root of n. So this converges as n goes to infinity in distribution or in law. So essentially, distribution means that the probability for each n on a set that result fall to the set is the same as the probability of the limit on the same set. And sets are usually taken, it's in distribution, so remember it's for all measurable sets with zero measure boundary. So this converges to the normal distribution. Normal distribution with zero mean, because we have subtracted the mean, and the variance sigma, the same variance. I will keep this because this we will have for comparison. So what essentially it means that if you put these points, take the sum of them, they start to fall closer and closer to each other, closer to the more points you take. So this is density with some 1 point, then it will be density with 2 points, 3 points, and so on. So they will accumulate near the mean. So if you stretch this function, it will go to the normal distribution. So the form of this function should go to the normal distribution. So let like 0, 1, it's something like this. This is 0.4 here, and something like 1 is here. The normal distribution. A very nice function which is concentrated more or less between -2 and 2 and go very fast goes. So what it is? So this is a normal distribution is a density which is so for sigma 1 it is a density. No, not for any sigma. So it's sigma square root of 2 pi exponent from minus x squared to sigma square. So see, it decays exponent of minus square very fast. Essentially, it's well, the fact that it decays very fast, it is actually a fine question because the convergence is not uniform. So it's essentially convergence here, not convergence far away. So that's central limit theorem, and this central limit theorem now can tell us what is the narrow of the computation. So how we do it? So we applied so we know that this function goes to this distribution. So the probability of having this smaller than something is the same as probability of having this smaller than something in a limit. So what we conclude is that the probability of exactly this term here, but now we can apply it for the, instead of x1, x2, xn, we take function at this point. So if x is a random value that IAD is x is IAD, then f of x is also IAD. So we take what? Modulus of 1 over n over sum f xi. So the difference between function and its approximation by the Monte Carlo method is smaller than, so say, sigma is coming into the play, right? So we put sigma here explicitly. And also there is square root of n, so we also put it from here to the left-hand side. And this is approximately in the limit n goes to 0 is given by the function which is a, so this is standard normal, this is cumulative distribution of the norm of this density. So essentially what it is, it's one, it's for sigma, so it's sigma we removed, so it's for sigma equal 1. So an integral from minus infinity to lambda of this expression. Okay. So let's make it explicit now. So quantitative. For example, taking lambda equal, so this is from more or less 2. We can compute this value. So then 0.95. So it means that the error of computation with Monte Carlo method is equal to this 1.96, so essentially 2 times sigma divided by square root n with probability so it's below, no, it's below, it's smaller than this with a probability 95%. So you cannot, with Monte Carlo method, you cannot guarantee the answer. It's only probability because all the points are probabilistic. So you can guarantee it with certain probability. So taking bigger lambda, the probability is bigger. But for example, taking this lambda, it gives you that if you want to have just 95% probability that your answer is correct, then you can, with Monte Carlo method, you reach this accuracy. Yeah? And you always reach this accuracy, whatever percentage you put, you always reach this accuracy, but just prefactor will be different. So it always square, or something divided by square root of n. So that means that error of Monte Carlo method is or n minus 1/3, more minus 1/2. So it's not so big number, but you see that independently of dimension. So from one hand side, it's rather low order method, just one half. Yeah, so it's order 1/2 instead of order 2, 4, and 5 that we could do with quadratures. But on the other hand, it does not depend on dimension. So there is this play. We see it after the break. Let's make a short break and then we can finish. 5 minutes. Okay, so now what we have is that having a certain domain in arbitrary dimension, you have to pick up random points. Uniformly distributed, well, uniformly distributed is not hard to do. Well, usually in typical situation, you take a cube and then integrate function essentially with a factor which is a characteristic function of this volume, which is, in other words, you pick up uniformly random distributed points in a cube, which is standard. It's given by the standard procedures, and you just ignore the points which are not inside the volume. Then it gives you a uniform distribution inside the volume. And we have the arrow of order n minus 1/2. So for example, for epsilon, the same epsilon as we had, 10 minus 3, we need n of order minus 1/2, no? 6 points. So we need million points in order to compute the integral for arbitrary dimension. Dimension doesn't matter. And you see that for dimension 10, it's certainly way better than the other. So you need many points, but comparing, so the Monte Carlo, which gives you n minus 1/2 versus quadrature, which gives you, so with this computation, it gives you arrow of order n minus 2 over d. So what you see, they give the same number of points if d is 4, right? So when a dimension is smaller than 4, quadrature is better. So up to dimension 4, you can use quadrature. But if dimension is bigger than 4, then Monte Carlo is better. And for high dimensions, it's enormously better because you see 10/15 versus 10/6. So the Monte Carlo method, though it is heavy, for high dimensions, it's probably the only way you can use then to compute the integral. Okay, so the next step is some modification of the Monte Carlo method, which is called quasi-Monte Carlo. Quasi-Monte Carlo methods, they use, so it's better in some sense. So instead of IID sequences, it uses deterministic sequences, but specially defined. It uses deterministic which have a name. So it's called, so they're called quasi-random. Or another name is the sequence of low discrepancy. endpoints. So I will give an example, explain what it is, but I think that we have one of the projects about random generation of random numbers and quasi-random numbers. So I hope we will have this information of one of the lectures in June. So to see how to generate random numbers, and hopefully we'll also see this idea of generation of these deterministic sequences. So that's actually has to do with algebra and dynamical systems. So the main property of this sequence, which essentially define what means this quasi-randomness, is that whenever you compute the mean value of the, let's compute the mean value with endpoints. Let's compute the mean value of the function f with endpoints. So it will be, so we approximate just in the same way. So we approximate the integral of f dx. So now, okay, let's make it in the interval. So from 0 to 1, just on a line. So we approximate it with a mean. So let's start with one dimension. Right? And the property is that the error of this approximation, so it's what? It is a difference, modulus of the difference between approximation. So this is approximation and the exact value. So the difference between the one and the other. And the difference should be smaller or equal than the constant by the mean of the absolute value for the derivative, right? By log n in some power divided by n for some c and k. So essentially I'm not giving details. So for some class of functions f, it should be designed such that the points have such a properties. So so essentially it takes a line, and instead of having uniformly distributed points, it starts to put points. So randomly, you put points randomly. But this method will throw points deterministically in different places in such a way that the error of the computation will be this. So log n power k divided by n. So usually you can achieve, so for some c, and so the typical method is k is dimension, okay. So somewhat you already see that this is better than Monte Carlo because it's essentially order n, first order method. So there is this bad logarithmic correction, but logarithm with large n, for large n logarithm doesn't matter that much. So essentially the denominator is important. So it's for large n, this is better than square root of n. That's good. So what it means, So it's not actually this is for arbitrary dimension. So I'm sorry. So this is general. In K, so you can define sequence that K is dimension -1. Minus or plus. -1. You see, if you have a, you can confused a bit. I think so. Just drawing this picture once again. So you have a domain. So normally for this, directly this method gives you the points in some domain. And Monte Carlo would just throw the random points. And this method will throw points which look random, but actually they are not random at all. They are given by a very specific formula. And but idea is the same. So these points, they appear everywhere in the volume in a rather dense form and uniform form, such that computing the average of the function gives you an integral. And unlike the random points, where the convergence is given by central limit theorem, so it's square root of n, here it's n, so it's faster. So it's specially defined sequence. So the example of such a sequence without a proof. So we start with 1D. So the example is, it's Halton sequence. Halton. Of low discrepancy. Points. So how is it defined? So let's start with d equal 1. So take a prime number. And represent any natural number in base P. So what it means that n equal, so it starts with some a m minus 1, a0. So it's like, for example, n equal 2 it's binary, n equal p equal 10, it will be decimal representation of a number. So, but p is, we take p prime. So what it means that all they belong to the sequence from 0 to p minus 1, and n is just a sum. So from 0 to m, ai. Correct. Hmm? And now, how we make a Halton sequence is just you invert it. So the Halton sequence points, so this sequence phi1, phi2, so are. So each phi n is just you invert. So you write the same base P representation, but now you put 0 point, and now you put them all in opposite direction. So if, for example, in decimal representation, if it was 123, this will be 0.321. So this is is just a sum of the same coefficients, but p minus I minus 1. And that's it. That's it. So for n dimensions, for d dimensions, for any d, so what you do, you take multidimensional Halton sequence. So what you do, you take d primes, so there should be co-primes, so they should be different. And then a sequence of this of point now in d dimensions is, so each point you take as, we take it one here, so each point is, you compute as one-dimensional sequence. But now each one with respect to its own prime. So you just do the same but different for each point, and then since primes are different, it is mixing. It gives this mixing effect in the dimension. So what you can see that this error, in this method, the error is, so it's log d minus 1n over n, and it is better for large n, even for large dimension, it's better than 1 over square root of n of Monte Carlo. And it's certainly better than the uniform lattice for large dimension. So this is how you compute high-dimensional integrals. There is one observation I can put. I don't know how much is it useful, but it's good for you to just to at least to make this exercise of computing probabilities. Existe uma sequência que é exatamente essa sequência, esse exemplo. Essa sequência tem essa propriedade. Yeah. You have to prove it. So it's rather non-trivial. So you see, it's a sequence is in large dimensions, which is sufficiently uniform, so that integral converges faster than just random points. So essentially, it takes care that the points do not come too close to each other, so that you lose accuracy with the random numbers. So it just takes care so that it's rather uniform. And then it converges faster. So this number, if dimension is high, this numerator can be large, but it's log. And log is always small. So with large n, and in Monte Carlo you usually take very large n. So the denominator wins. So it also wins with square root. Oh, okay. So what I wanted to say. Yeah. So sometimes you can some small observation, some improvement. When f of x can be approximated by a known function, by a function rho of x. Well, this is density, so it should be f of x divided by integral f dx. So that mean is 1, for which is a density function, probability density rho, for which we can generate random numbers. Well, so assume the situation that you want to compute very accurately high dimensional integral of some function, but function you know. And you know how to compute random numbers of this function with this density or with density of this function or something very close. So that helps. That helps in the following way. So then what we do is we compute. So now numbers will be just the same. Yeah? So now these are not uniformly distributed numbers. These are distributed with density rho. So that means that integral, I will not write the domain. Okay, I write it first time, but so the integral, what you can do, you divide it by rho and multiply by rho. So now this is the mean value of this function. So this function we know. So with this. And this can be approximated already by the sum, just as we did. So we compute this sum instead of the sum without. So we add the denominator, and so what we gain is that is an arrow. So the variance so remember that so arrow is given by the central limit theorem with variance sigma square of this function. So we need to compute variance of this function to see what is an error of the. So we had the formula with the central limit theorem that gives you, so with certain probability, the error is smaller than certain number, and it depended on the variance. So let's see what is the variance for this particular value, this choice. Arrow of, we're back to Monte Carlo. So the variance, so let's compute the variance. Sigma square is what? It is the integral of the function minus its mean value square. And I take mean value of the whole stuff. So we have to multiply by density function, dx. Okay, so now we can open this. So how you do it? I'm doing now the very standard computation. So now we take the first one. Open the square. So it will be f over the rho square by rho. So if f square rho dx minus twice. So this is just constant by this by rho. So that will be integral of f dx. And then there will be this part. So will be plus f by rho mean squared integral rho dx. So this is 1. Remember this, what we computed is the mean. Right? So this gives a square which cancels one of these. Square. This. Okay, now we substitute here that rho is this. Is approximately f divided by integral of f, which is f divided by, again, if this is f over rho, just f over rho, right? So this has become approximately, so we put it here, so it flips. The coefficient comes out. One of the f's will be cancelled. And again, this is f over rho mean. And you see everything cancels. 0. So what we get is that rho square, the variance is 0. So this is higher order method. So the error is actually should be given by the next order approximation. Okay, for the actually the central limit theorem already doesn't is not useful here because well, it's useful, but with much smaller variance, So it's not exactly 0, but. I'm a bit confused. Okay. Yeah. So that it means that. Bit confused, but okay. So think about this a little bit. So essentially, if you know the function, you can play with the method how to make it better. But this depends, of course, on if you can achieve this distribution of the special kind. But anyway, the central part is that there is a Monte Carlo method, which you just take random numbers in your domain, some values of function, you get a result. So this is a somewhat very easy method how to compute integral, just a couple of lines of code. Just generate number, compute function, sum. Number, compute function, sum. And it always works with certain probability. So now you don't have anything completely certain, but you can have a certain with any probability you like, taking and any accuracy you like, taking the sufficiently many points. For lower dimension, it works, but not very efficiently. You need many points. But for high dimension, it is very effective. So it's much effective than taking these grids, uniform or even adaptive in computers. So that's it. And so let's. I think that what we proceed to now. Next, I will start initial value problem for differential equations. Which is so like 3 lectures at least, and then we probably have one more lecture in June. So let's schedule the test for the first Friday in June. So this should be June 3. Good. June 3 we'll make a test here, presential. Okay. So thanks.